Hi, I'm Mark Barsamian. In this video, I'll be discussing three kinds of bank account interest: simple interest, periodically compounded interest, and continuously compounded interest. The reading for this video is from section 3.1, the constant E in continuous compound interest, more specifically from the bottom of page 181 to the top of page 185, examples 1, 3, and 4. And the homework is this collection of problems from section 3.1. In this video, we'll explore ways of computing interest on bank accounts. We'll begin with the most simple type, called simple interest. Then we'll discuss a more complicated type called periodically compounded interest. And then finally, we'll learn about continuously compounded interest. It's all very concrete stuff, but along the way, something amazing happens. We see that that number E discussed in the last video shows up. So first I'll talk about simple interest. To say that a bank account has simple interest means that the interest is computed only on the amount of the original deposit. An account with simple interest has an account balance described by this equation. Capital A equals capital P plus capital P little r little t. In this equation, capital P is the amount of the original deposit. That's called the principal. The number little r is called the interest rate, and it's expressed as a decimal. The number little t is the time in years since the original deposit. And finally, capital A is the account balance at time little t. Now note that the equation above is solved for A in terms of P, R, and T. So it describes the balance as a function of P, R, T. In function notation, we would write this. Capital A parentheses T equals that stuff. Let's think about the graph of this function, A parentheses T. That equation has the form of a line equation. The slope would be capital P little r, and the y-intercept would be at the point 0, comma p. So the graph would look like this. Let's do an example. Example 1, you deposit $1,000 into a bank account with 3% simple interest. The question is, what's the balance after 7 years? And then question B is to illustrate the result with a graph. Well, remember that we have this equation that describes simple interest behavior. Now let's think about what letters we know values for. This 1,000 is our value of P. This 3% tells us that little r is 0.03. We're told 7 years, so little t is 7. So the question is, find A, find the balance. Okay, well, we'll use our formula. So the answer is that after 7 years, the balance will be $1,210. Now I want to discuss what's called periodically compounded interest. For a bank account that has periodically compounded interest, the interest is initially computed only on the amount of the original deposit. So the account initially behaves just like an account with simple interest. But after a certain time interval, the interest that's earned is added to the principal. And then from then on, the interest is earned on the larger pot of money. This is called compounding the interest. The compounding happens repeatedly at regular intervals. So it turns out that an account with periodically compounded interest has a balance that's described by this messy equation. Now in this equation, capital P is the amount of the original deposit, it's called the principal. Little r is the interest rate, expressed as a decimal. Little t is the time in years since the original deposit. This new symbol M is the number of times per year that the interest is compounded. And then A is the account balance at time t. Now, actually, this formula can only be used to compute the interest at the exact times when the interest is being compounded. In between those times, the interest is being earned as simple interest on a certain amount of money. So the account balance will grow like the balance of an account with simple interest. So in other words, the graph will be a segmented graph. So if we think about the graph, again, it would start out looking like the graph of an account with simple interest. But at a certain point in time, the interest gets compounded, gets added to the amount of the principal. So in this first chunk of the graph, the slope is m equals PR, capital P, little r. You're earning interest on the amount of the original deposit. But at this point in time, the interest gets compounded and gets added to the principal. So now the pot of money that you're earning interest on is larger. So the graph is going to grow with a steeper slope. So instead of following the original trajectory, the graph will be a little bit steeper. So this slope is now not capital P, little r. It's going to be a larger amount of money in place of the number capital P. Now, at some point, though, again, the interest will be compounded, and so the graph will stop following that straight line trajectory. So instead of continuing like this, the graph will break and go a little bit steeper, and so on. So that's how the graph goes for an account with periodically compounded interest. So let's do some examples. In this example, we're going to have $1,000 deposited into a bank account with 3% interest, and we're going to wait 7 years, just like we did in the previous example. But in this example, the interest is compounded periodically. And we're going to do this with 3 different compounding periods. Question A, the interest is compounded yearly, so once a year. In question B, the interest is compounded monthly. And in question C, the interest is compounded daily. So we have to find the balance. Well, as in the previous problem, this 1,000 tells us that capital P is 1,000. This information tells us that little r is 0.03. And this information tells us that little t is 7. What else do we know? Well, in question A, the interest is compounded yearly. That tells us that m is the number 1. In question B, the interest is compounded monthly, so that tells us that m equals 12. The interest is compounded 12 times per year. And in question C, the interest is compounded daily. So in other words, m is 365. Now in all 3 questions, we're supposed to find the balance. So the balance is unknown. All right, well, let's use our formula. Our formula is there. So notice I took all of those numbers that we know and I populated that formula with those numbers. Now, our instructions are to give exact answers in symbols and then decimal approximations, rounded to 2 decimal places. So we're going to use a calculator to get the decimal approximation, and the calculator is capable of doing this entire calculation. So I'm just going to leave that as my exact answer. Now let's type that into a calculator and see what we get. So we just type in the formula. Now, it may seem silly to have included things like 0.03 divided by 1. I could have just written that as 0.03. But I wanted to show you how you can really just type in these complete formulas. Now, notice the result is roughly $1,229.87. Let's do question B. Question B is the same thing, but using m equals 12. Well, I'm going to copy down this whole thing that we just did and just repopulate the expressions. So instead of m equals 1 in question A, in question B, we're going to have m equals 12. So that means that I put a 12 here, and in the exponent, I put a 12 here. So there's my new exact answer. Let's get our new approximate answer. Well, it turns out if you go to Wolfram Alpha and you type in these numbers, we get roughly 1233.35. Okay, let's do the same thing for question C. Let's just copy down the work that we just did and change the value of m. So instead of m equals 12, we need to have m equals 365. Well, when I type all that into Wolfram Alpha, I get roughly 1233.67. So you see the style of using a calculator that I prefer. I like to write down the full expression that I'm going to type into the calculator on paper and then type it in. So the very last step of a problem where I'm using a calculator is the calculator step. All the other steps are by hand on paper. Now let's look at the results of these examples. Notice that when we compound more frequently, well, in example 1, we never compounded. And then in example 2, we compounded with m equals 1 once a year, with m equals 12 every month, and with m equals 365, compounding daily. The results that we got were $1,210, and then these amounts that were going up each time. So see if we can visualize this with a graph. I'm going to try to put all of these on one graph. So the result of example 1 was just a straight line graph. And the y-intercept was at 0, p, and at the end, the coordinates of the final point are 7, 1210. Just one straight line. Now what about the case where we're compounding yearly? That one I can draw. I'm going to draw that one in red. So that graph starts out looking like the graph that we just drew, but at time 1, it breaks and goes a little bit steeper. At time 2, it breaks and goes a little bit steeper still. At time 3, it breaks and goes a little bit steeper still, and so on. So for compounding yearly, the final balance was 1229.87. Now I didn't draw this to scale, but I wanted you to see the idea of the compounding and how it results in a higher balance. Now I want to think about how this graph would look. Now this is going to get really crazy because this graph follows the original graph only for 1 month and then breaks and goes a little steeper and then breaks again and goes a little steeper. So this graph is going to have a lot more frequent breaks, and that's why it ends up being higher. So again, that's meant to be a bunch of line segments. Of course, there would be 84 line segments, so many of them that you couldn't really see them as segments. And you could imagine the curve that has m equals 365 is going to be really a lot of little segments. Of course, the balances don't go up very much the more we do this. So notice that the more frequently we compound, the higher the resulting balance gets. But also notice that as we compound more and more frequently, the balance doesn't go up much more. So it went up from $1,210 to $1,229.87 just by compounding once a year. Compounding once a month got us a final balance that was about $4 more. Compounding every day only got us an increase of about 30 cents in the final balance. So an obvious question is, what happens to the balance? What happens to the value of that expression when you compound more and more frequently? That is, as m goes to infinity. That is, what's the value of this limit? The limit as m goes to infinity of that expression. That's the expression for the balance of a periodically compounded bank account. Remember that in the previous video, we discussed this limit. That's a similar looking limit. And we found that that limit had a value that was the number e, roughly 2.718. And we discussed that when you put an x inside that limit, and you take the limit, you get a function as a result, e to the x. Well, it turns out that if you do another change of variables, the limit that we're interested in is capital P e to the RT is the result. So that's an exponential function. I would like to do something. I would like to look at the graph of this thing that just emerged from taking this limit. And I would like to look at the graph of this compared to the graphs of the account balances for the interest types that we just discussed. So I'm going to copy that ugly graph that I just drew, and I'm going to put it on the next page, and when we scroll down, we'll find it there. Well, it turns out that the graph of y equals capital P e to the RT looks like this. It has a shape very similar to those other graphs, and in fact, as you compound more and more frequently, these other graphs seem to be getting closer and closer to the graph of y equals capital P e to the RT. So now remember how messy the formulas were that describe these graphs. It was the horrible formula for periodically compounded interest. By contrast, look how simple that formula is. Well, this gives us an idea. Well, it gives me an idea. Let's use this formula to describe the interest of a new kind of bank account. So we're going to invent a new kind of bank account that uses this formula to compute its balance. And we're going to call it continuously compounded interest. So an account that has that kind of interest has a balance described by this equation. And in this equation, capital P is the amount of the original deposit. That's called the principal. Little r is the interest rate expressed as a decimal. Little t is the time in years since the original deposit. And capital A is the account balance at time t. So as our first example, let's do an example that has $1,000 deposited into an account with 3% interest and wait 7 years. This time, the interest is compounded continuously. The question is, what will be the balance? And we want to answer in symbols and then a decimal approximation. Well, as in previous examples, I want to make sure that we understand what symbols we know and what symbols we don't know. We're supposed to find A. We know that capital P is 1,000, little r is 0.03, and t is 7. So let's just populate this formula with those numbers. And there's our answer, our exact answer. We can type this into a calculator and get a decimal approximation. Let's go up and compare that to our previous numbers. Remember that when we compounded daily, we got $1,233.67 for a deposit of $1,000 at 3% interest, waiting 7 years. So when we compound continuously, we only get another penny. So these graphs of compounding periodically are really getting closer and closer to that red graph, and the red graph is not much higher than those. Let's go on and do some more examples. In the next few examples, we're going to be solving for different variables. This equation, capital A equals P e to the RT, has 4 letters, and it's solved for A. The equation can be solved for each of the other letters, as these examples will show. So example 4, which is similar to number 27b, $937 is deposited into an account with 2.3% interest compounded continuously. And the question is, how long after the initial deposit until the balance has grown to $1,200? So I want to start by identifying what we know and what we don't know. We know that P is 937. That's the amount of the original deposit. That tells us that R is 0.023. This tells us that capital A is 1,200. And the question is, how long? So T is unknown. So my approach to these problems is to start by solving the equation for the correct letter. So I'm going to write down my steps and write down the results. The first step, I'm going to divide by capital P. The result of that step will be this new equation. The next thing I'm going to do is take the natural log of both sides. The reason I'm going to do that is because a rule of logarithms that says this. ln of e to the x is x. So on the right side of this equation, this simplifies to just simply RT. Now I'm going to divide both sides by R because I'm trying to solve for t. The result is t equals ln of the quantity, capital A over P, divided by R. So now we're going to populate that formula with these numbers. That's my exact answer. Let's type this into a calculator to get a decimal approximation. And the result is that the time is approximately 10.7 years. So there is an example where I solved the equation for t in terms of the other variables first, and then I plugged in my numbers. Let's do another example. Example 5. Deposit some money into an account with 2.3% interest compounded continuously. The question is, how long until the balance doubles? Well, what do we know and what do we not know? Well, notice there's no mention of the principal. It just says some money. This tells us that little r is 0.023. Now, the fact that the balance doubles tells us that capital A is unknown, but we do know that the balance has doubled from the original. So whatever P is, capital A is twice whatever P is, because the balance doubled. Now, what about time T? T is also unknown. So we have 3 unknowns in this problem. But what are we being asked for? We're being asked for T. So we should use the form of the equation that's solved for T. That form is this. T is ln of the quantity, capital A over P, divided by R. Let's plug in the stuff that we have written above and see what happens. Look, I put in my stuff, and I end up with this expression inside that logarithm. Notice that the P over P cancels. We can cancel that P because P is not 0. And look, there's our exact answer. We can type this into a calculator. I used Wolfram Alpha and get the answer 30.14 roughly. So that's our decimal approximation. And I used Wolfram Alpha for that. So in our previous problem, I should have also pointed out that this is our decimal approximation. So the exact answer is the one that has the ln symbol in it. the decimal approximation is the one that has decimals. The only way to write the answer exactly is this way. Let's do one more example. Example 6. Suppose you want an account with continuously compounded interest. You want it to double in 20 years. What interest rate will you need? The book would ask this: at what nominal rate, compounded continuously, must the money be invested? Well, let's think about the letters that we know and the letters that we don't know. Capital P, that's the amount of the original deposit. We don't know what that is. What about little r? It's unknown. What about the value of A? Capital A is unknown, but we do know something, that capital A is 2 times capital P because the money is doubling. And we know that the time is 20 years. So we have 3 unknowns in this problem. But the thing that we're being asked is the interest rate. So we're being told to find R. Well, so we have to solve the original equation for R in terms of the other variables. Now, the solution of that equation is going to unfold very much like the solution of the equation for the letter T. Earlier, we did this computation. We solved that equation for T, and we got that. T was that expression, ln of capital A over P divided by R. Well, in the current problem, we're solving the equation for R instead of T. So the only difference is going to be in this last step. Instead of dividing both sides of that equation by R, we're now going to divide both sides of that equation by T. So there's our equation solved for the letter R in terms of the other letters. So now let's plug in our values. Notice the P's canceled as they did in the previous problem, and we have our exact answer. It's ln of 2 divided by 20. We can type this into a calculator and get an approximate number. I used Wolfram Alpha. Now we're supposed to give the interest rate as a percent. So the final answer is not the value of R. The final answer is the interest rate. So the interest rate is 3.47%. The value of R is 0.0347, but we were asked for the interest rate, and that's usually quoted as a percentage. So that's the end of the example. That's the end of the video. Thank you.